In this video, we're going to talk about repeated addition and repeated multiplication, or in other words, multiples and powers. We're going to define these in the setting of a ring. So let's assume R is a ring, and let X be an element of the ring. All right, first of all, let's talk about repeated addition. So we define n times x for an integer n as follows. All right, so first of all, I want to point something out. Here I am using the symbol dot for multiplication. That's because I'm not doing multiplication within the ring. Let me write this down. So this is not necessarily multiplication within R. After all, n is an integer, but x may not be an integer. X may be something like a matrix. In the last video, we talked about how 2x2 matrices with real number entries are an example of a ring. So x could be one of those. And we're multiplying now by an integer. So here's what this means. First of all, we define 0 times x to be 0. Now there's a fine distinction to be made here because there's two different zeros in this equation, and they represent two different things. The first one represents the integer 0. The second one represents 0, the additive identity of the ring. In fact, I might go ahead and put that in this equation here. So what we're saying is that if x is a ring element, any ring element, and we multiply that by the integer 0, that gives us the additive identity of the ring. That's part of our definition. The other part of the definition, or the next part, is if n is a positive integer, then n times x is equal to the sum x plus x plus x plus x plus x plus x n times. So for example, 3 times x, even if x is something weird like a matrix or a polynomial, that means x plus x plus x. Okay, we can define this more formally inductively by saying if n minus 1 times x is defined, then n times x is defined to be n minus 1 times x plus another x. Okay, you don't have to pay attention to that inductive definition most of the time, but if you ever need a formal definition that doesn't rely on drawing an ellipsis and saying n times or n copies of something, this is it. All right, and finally, if n is negative, then here's how we define n times x. So what would it mean, for example, to take negative 3 times x? The way we define that is we make that to be absolute value of n copies of the opposite of x. So for example, negative 3 times x would be 3 times the opposite of x, which would be opposite of x plus opposite of x plus opposite of x. So that's how we define integer multiples of a ring element. And again, that's not multiplications happening within the ring. When I write this center dot here, that multiplication dot, that does not represent the ring operation of multiplication. It represents something else. However, if we are in a ring where 1, 2, and 3 are elements because our ring consists of numbers, it's going to turn out that this definition here, this notation, is consistent with ring multiplication. So for example, if I have a ring that contains the integers and it contains unity, and actually let me rewrite that. So if I take that identity, the multiplicative identity, multiply that by x, well, that's equal to x because that's what it means to be the multiplicative identity in a ring. But if I take 1 times x, where 1 is the integer 1, then that by definition is just x. Okay, and those two things are the same. So my point is that this distinction between multiplying by an integer and multiplying by a ring element, it's not something we're going to have to be super neurotic about most of the time, but there will be cases where the two are different. Like if, for example, R is the ring of matrices, 2x2 matrices on the real numbers, then I can certainly multiply a matrix by a matrix, and I'm just making up an example here. And I can say what that would be. I'm not going to say right now, but it would be a 2x2 matrix. But I can also multiply this same matrix, 0, 4, 5, 1, by just an integer, like 4. And that would be the result of adding this thing to itself 4 times. And that would come out to 0, 16, 20, 4. Same thing that you would get by multiplying the matrix by a scalar in linear algebra. They behave the same way. Okay, so that's repeated addition. And the repeated multiplication, I don't think I need to say a whole lot more about, really, because it's the same as what we did in group theory. So for repeated multiplication, if x is a ring element and n is a positive integer, we're just going to define positive integer powers for right now. Then we define x to the n to be x to the n equals x, where there are n factors here, n copies of x. Okay, notice I'm trying to avoid using the multiplication dot there because I'm using that for now to represent multiplication by an integer, which is repeated addition. And here I'm doing repeated multiplication within the ring. This is the ring operation, x times x times x times however many x's I need. Again, I can formally define that by saying x to the first is x, and then assuming that x to the n minus 1th power is defined, I can define x to the nth power to be x to the n minus 1 times another x. And that is, again, an operation taking place in R, the multiplication operation in R. You may wonder, though, why did I only define this for positive integer n? With a group, we were able to define powers for any integer, including negative integers, including 0. Well, here, think about, just from your prior mathematics experience, what you might expect x to the 0 to be. Usually we take x to the 0 to be 1. In a ring, I don't know that I have unity. I don't know that I have a multiplicative identity. So I don't have anything yet that I'm comfortable calling x to the 0. Once we start talking about rings with unity, I will go ahead and define x to the 0th to be the identity. And negative powers, those are just out of the question right now. A negative power of x would involve knowing a multiplicative inverse for x. And in some rings I will have that frequently, and in some rings I will have that very rarely. So in a general ring, if I know nothing more about its structure, like it having unity or having multiplicative inverses, the best that I can do is define positive powers of x. Okay, so that's repeated addition and repeated multiplication. I'm going to mention one more thing here that just goes along with this theme, and that is the idea of the characteristic of a ring. Sometimes you'll have a ring, so I'm going to just subtitle this over here, characteristic of a ring. So sometimes you have a ring, and let's take here for an example z mod 4. Okay, and that ring has addition and multiplication, so it's z mod 4 under the usual operations of addition and multiplication. There I am using the dot just because that's what I usually call multiplication in z mod 4. All right, this ring has a special property. So imagine your favorite element of this ring. I know that mine is 3. And imagine adding 3 to itself multiple times. If I were to do this, is there any number of times I could add 3 to itself and end up with 0? And the answer is yes, I could add 3 to itself 4 times, and that would get me back to 0, the additive identity for R. And actually, that would be true for any ring element. I could add 2 to itself 4 times. Actually, I could add 2 to itself 2 times and get 0. But there's a point I'm going to make about the entire ring. And I want to keep track of how many times I have to add any element to itself in order to guarantee that I get 0. One thing I see here is that I can add any element to itself 4 times. So for every x in this R, for every x in this ring, 4 times that x, and again this 4 means the integer 4, not the 4 in z mod 4, 4 times x is equal to 0. That's true for every x. And again, if I picked x to equal 0 or 2, then a smaller multiple would have worked. But this number 4 here works for every x in the ring. And 4 is the smallest positive integer with this property. It's the least positive integer with this property. If that is the case, if there's a positive integer such that that multiple of every ring element is 0, and that's the smallest positive integer of that property, then this integer gets to be called something. In this case, 4 is called the characteristic of the ring R. We'll see that word later on. We often use it with respect to fields. A field, again, is a ring where every non-zero element has a multiplicative inverse and the ring is commutative. Fields are interesting with respect to characteristics, but a ring that is not a field can also have a characteristic. In this case, the characteristic is 4. And in general, might as well state this now, Z mod n has characteristic n for each positive integer n. So just something to file away for later use. Okay. In other words, if I look in Z mod n, I take any element of Z mod n and add it to itself n times, I will get 0. Okay, so in that way, it's kind of like thinking about the order of a group, but it's not exactly the same as the order of a group because we're not just counting a number of elements here. The characteristic is not n because that's the number of elements. It's n because that is a integer multiple I can take of every element and get 0. Oh, and one more thing before I wrap up, because I've defined what it means to have characteristic a positive integer. That means that positive integer is the least positive integer that I can add every ring element to itself that many times and get 0. But what if you can't do that? Like, here's another ring, Z, and if I just take some integer in Z, like 3, and think, okay, well, what times 3? What integer multiple of 3 would give me 0? Well, there isn't really any. I mean, there's not one with a positive integer in anyway. This would be true. It would be true if n was 0, but that's the only way that would be true. There is no positive integer number of times I can add 3 to itself in the integers and get 0. So in this case, if there is no n in Z plus such that n times x is equal to 0 for every x in the ring, then we say the ring has characteristic 0. And a useful way to remember that is an integer that I can multiply by every ring element and get the additive identity in my ring. Okay, so anyway, that was a brief intro to repeated addition, or the idea of an integer multiple of a ring element, the idea of a positive integer power of a ring element, and the characteristic of a ring.